the next result says that, so we have this theorem, so we have this corollary. It states that any irreducible polynomial f of x over a field of characteristic 0 over a field of characteristic 0 has simple roots. Also, any irreducible polynomial f of x over a field f of characteristic p, and p is not equal to 0, right, has multiple roots. This has multiple roots if and only if there exists some other polynomial g of x in the given field f of x such that this f of x is nothing but this polynomial g of x raised to power p. So this is, if you see, this is a very strong result. It clearly say that you have two cases. One is when the characteristic of your field that is given to be 0. In another case, it says the characteristic of the given field f that is given to be p, which is not equal to 0. So in this case, you would have simple roots, and in this case, you will have multiple roots. If and only if the condition here is that the polynomial would be of this kind, g of x raised to power p. So let us see the proof for this theorem. The proof is very simple, right? So it says that for that we assume some polynomial. So let f of x, which is given to be a polynomial of this kind, a0 plus a1x plus a2x square plus up to so on an x raised to power n. So we can write this polynomial as summation I varies from 0 to n ai x raised to power I. So this is the polynomial. So let fx of this kind be an irreducible polynomial over f, irreducible polynomial over f, and all the coefficients belong to this field f. So according to the theorem that we have just seen previously, so by the result that we have seen, this polynomial f of x has multiple roots. Whenever this has multiple roots, if and only if its derivative is equal to 0. So let us first calculate the derivative for this. So what would be f dash x? F dash x would be, this being a constant, it would be 0 plus its derivative would be a1, and then its derivative would be 2a2x plus so on, plus we have the last derivative as n x raised to power n minus 1, right? So we can write in summation the derivative as summation I varies from 0 to n I. Here you see the subscript is 1, here also we have 1. If we have 2 here, we have 2 here, and the power is 2 minus 1, right? The power is 1. And here we have n, and the power is n minus 1. So we have I varies from 1 to n, not from 0 to n. So I that varies from 1 to n I ai x raised to power I minus 1. So this is the derivative, and according to this result, if we have multiple roots, then the derivative is equal to 0. Then this derivative is equal to 0. Now, when does a polynomial equal 0? Polynomial. So this is also a polynomial. This is a 0 polynomial. So that means you can write this polynomial as 0 plus 0 x, right, plus 0 x square plus so on 0 x raised to power n. So we can equate all these coefficients equal to the coefficients for this polynomial. This is the 0 polynomial, right? So we have 0 is equal to 0, then we have a1 is equal to 0, then we have 2a2 as equal to 0, and so on. So that means from here we can say that this I into ai would be equal to 0 for all I lying between 1 and n. So this would be true, right? So now if we have two cases. So for the first case, if we assume the characteristic for this field f, the characteristic of this field f is equal to 0. So what does it mean? It means that we do not have any n such that n into the multiplicative inverse, the multiplicative identity, that becomes 0. So we do not have any n of this kind. So this won't be true in this case. So we only have 0 into 1 is equal to 0 in this particular case. So this is the field with characteristic 0. So that means here, if you multiply ai with any other element I, so you won't be able to get 0 until and only we have ai is itself equal to 0 for all I present between 1 and n. So that means if all the i's from 1 to n are 0, so that means we would have a1 is equal to a2 is equal to up to an that are all equal to 0. If they are all equal to 0, so our polynomial f of x, which was a0 plus a1x plus up to an x raised to power n, becomes nothing but a0, which is a constant. But this thing won't be true. Why? So that means it would be belong to f only. But this is a contradiction, which is a contradiction. Why? This is a contradiction because this f of x belongs to capital F of x. This is a polynomial and it is not a single scalar number. So that means here in this case we have a contradiction. What we have supposed is incorrect. So in this case, therefore our assumption that the polynomial has multiple roots, is incorrect. So in this case we have a single root for the given polynomial f of x. So this is the first part. For the second part, for the second case, we assume that the characteristic of the given field, suppose the characteristic of the given field f is equal to p, where this p should not be equal to 0. If this is equal to 0, we would have the case 1 only with us. So now in this case, if we wanted to have multiple roots, so for multiple roots, what is the criteria? According to the result, the multiple roots of this polynomial is present if and only if its derivative is equal to 0. So what was the derivative? Derivative was I varies from 1 to n, I ai x raised to power I minus 1. So this was the derivative, this is equal to 0. So that means when we equate all the coefficients here, so we would have either we would have this ai should be equal to 0. So now because the field has characteristic p, so we have these two cases. One is these ai's, they are themselves zeros, and the second case is this I is this I divides p, the characteristic of S. So that means you can say this I is some multiple of p that is divisible by p. If you have say a field, if you have a field of characteristic say 5, then in that case 5 into anything, say a, this would be equivalent to 0. So this would be equivalent to 0. Why? Because we are now in a field with characteristic 5. So similarly, if this I is divisible by p, so that means I into something else, that would be equal to p. So that means this p divides I. So in that case also this would be equivalent to 0 mod p. Right? So this is the property for characteristic and modulo p. Right? So this I would be equal to MIP. So if we have AI is equal to 0, we have a contradiction. Why? Because if AI is equal to 0, then we would have fx as only the a naught, and this is not possible because our fx was there in this polynomial field, right? So what if we have I is equal to MIP? So in this case, our f of x, which earlier was I varies from 0 to n, ai x raised to power I. So this was the given polynomial. So here we can substitute the value of this parameter I. So we would have MIP varies from 0 to n, and instead of this I, we would use MIP, and instead of this x raised to power I, we would use MIP. So we have just replaced the value of I in this particular expression. So let us see what do we have. So we can simplify this. So summation I varies from summation MIP varies from 0 to n. We have a MIP x raised to power p whole raised to power mi. So that means you have written this polynomial as some polynomial in x raised to power p. So let me call this as g of x of p. So this is what we were intended to prove, that for a field having characteristic p, if we have multiple roots, if we want multiple roots, so in that case your polynomial f of x should be written as some other polynomial where instead of x you have x raised to power p. So this is the result that we intended to prove here.